So what we'll need to think about then is how we use binary and why we care about binary. And the reason we care about binary is because we can manipulate it easily with something called gates. And gates, as we have here, are basically just this magic hat. And you put in something and you get out something else. In this case, we put in binary data. So we put in a logic high, we're going to say. You can just arbitrarily give it, and you put in something else, say a 0, and you get some output. And you can put in different values, and you'll get a different output. So how we know what's going to happen is we use what's called a truth table. So for any particular gate, and we'll give it a name to the magic that's happening, say an OR gate, and we'll say that when either of those inputs is 1 or high or true, the output is always true. So if we had 0, 0 going in, we'd get 0. But as long as one of those is high, the output will be high. So if the other one's high, if this is 1 and that's 0, then it's still 1. So this logic we call an OR gate, and we write it down in a truth table. So here we just say for each input, every possibility, we give what the output is. So if the input is 0, 0, the output is 0. If one of the inputs is 1, or both of them, the output's always 1 in this case. So the name we give that is OR, because if one or the other is 1, the output's 1. And you can think of that, if you're building the circuit physically, it might look something like this. So we have 2 switches. If one of those switches is closed, power will flow and light up the bulb. So if that one's closed, power flows, lights up the bulb. That one's closed. And if they're both closed, it still lights up. So that's physically how you might build an OR gate. So when I show a representation of it, I'm going to be showing 4 things really now. We'll have a symbol here. And this is on schematics, how we're going to show what an OR gate looks like. So we have 2 inputs to it, A and B, and again, this is what we were showing here. I'd call this one A and this one B. 2 inputs and 1 output. So in time, we have 0, 0, and 0. And this is shown on the waveform at this point. So we have 0, 0, and the output is 0. So that's here. Again, the next point, 0, 1, 1 for the OR gate is shown at this point in time. So we have 0 there, there's 1, and the output's 1. And you can read through that. Your input's 1, 0, and the output's 1. And that's that line in it. So throughout the course, you'll sort of see all of these representations being used. You'll see the waveform style, and you'll see the truth table. So it's good to be familiar with all of them. And this final piece of information is the equation for it. So here the plus symbol is actually meaning OR. So in this class, for the most part, we're going to be dealing with what's called Boolean algebra. And Boolean algebra is just another way of writing down all of the same information. So you can either write this symbol that says it's an OR gate when A is 1 or B is 1, the output's 1. This way is saying when A or B is true, the output's true. So the OR gate's just one of several sort of basic entities we have. The next one is the AND gate. And the AND gate's output is high only when A and B are 1. So again, we have the same input waveform as before, except for the output. The only state where the output is 1, I should say, is this final entry here. So the output's 1 only when both inputs are 1. So using Boolean algebra, we have the output y is A and B, and y is true only if A and B are both true. So that's another of the basic gates. Sort of the final one of the three very basic gates we'll talk about is the NOT gate. And the NOT gate, the output is simply the inverse of the input. So when the input's 0, the output goes to 1. When the input's 1, the output goes to 0. So y is not A, basically. And so here, we show this by just putting a line over it. So if we put a line over something, it means the inverse of the output is the inverse of the input.